Okay, welcome back. We've now arrived at the modern era. We've traced thinking all the way from Plato through the start of the modern era. Galileo with the first rather crude experiments and the invention of gambling math, also known as probability theory, which epistemologically rehabilitated induction, or to say it another way, helped gain credibility for conclusions that are arrived at by experiment and observation rather than by logic, math, and theory. You know, epistemologically rehabilitated induction. One of the nice things about becoming familiar with critical thinking is that you can look smart by using big words like that. Of course, if you're going to use big words, you need to be able to define them when people ask, because without definitions, words are not so much good. But we've arrived at the modern era. After epistemologically rehabilitating induction, now, thanks to gambling math and to picking of low-hanging fruit by Galileo, now we can do science. You know, that thing that's sort of responsible for most of the advancements in the modern age. That thing. It's really important. How do we do it? At a technical level, science gets really complicated. It involves a lot of technique. And you can spend your whole life studying that stuff. So I'm going to take a smaller project, just looking at more the episteme. What an abstract science is. Science is arriving at conclusions or getting towards knowledge that we're pretty sure of, not perfectly sure of, but pretty sure of, by experimentation. The application of reasoning to empirical observation and experimentation is what science is. Okay, observation, watching things, that one's not too hard. You've been doing a lot of observation so far, watching. But experiments, what are they? They're actual... Okay, experimental design is very important. If you get it wrong, it's like when you have biased statistics, except probably even worse. So it's very important, and finding the errors in experimental design is not always easy. So it's important and it's hard when you actually try to do it. But in general concept, experiments are not so inaccessible. You can figure them out. It's when you have two groups, you do one thing to one of those groups, and then sit back and watch the outcomes. Do the two groups end up having outcomes that are the same, or outcomes that are pretty different? And maybe we can also change venue a little bit to avoid the lexical interference. And you do one thing that changes the initial conditions in two groups, then you watch both groups and see if their outcomes are the same as each other or different than each other. And then you make the inductive generalization that difference in outcomes, if there is one, was due to the difference in initial starting conditions. And inductive inference. That's based, and it's not based on just observations that you just happen to see in your experiences. You actually deliberately create new experiences. You get those two groups, and you do one thing to one of them, do something else, or nothing, probably nothing, to another, and watch what happens. You create you're not just sitting back looking for examples, you're creating the examples from which you do inductive reasoning. So, let's say I wanted to know whether Zicam prevents colds. Well, I'd get a bunch of people, separate them into two groups, give both groups cold viruses, sneeze on everyone, and give only half the people Zicam medicine. Or Zicam. And then sit back and watch what happens. 3 things could happen. Well, okay, some of the people in each group are going to get sick. And 3 conclusions are possible. Zicam prevents colds. Zicam does nothing. Zicam makes colds worse. Those are the 3 possibilities. And we can evaluate between those 3 by comparing the relative numbers of people who get colds between the 2 groups. If the group that got Zicam gets fewer colds than the group that got no medicine, then Zicam probably prevents colds. Maybe the 2 groups are equal, or pretty close to equal. Looks like Zicam's worthless. It doesn't really do much of anything. Doesn't prevent colds. Maybe even the group that got Zicam gets more colds. They do worse and get sicker than the group that got nothing. Maybe Zicam's a poison. Those are 3 conclusions. Prevents colds, does nothing, is poisonous. And we decide which conclusion we jump to by looking at the spread in the outcomes between the 2 groups. Looking at the difference in how many people actually get sick. A difference in outcomes. Separate subjects into 2 groups, do different things to each group, and look for differences in the outcome. That's the basic recipe for an experiment. Okay, that's good. A lot of times, especially in medical literature, when you see experiment, people actually say RCT, or short for randomized controlled trial. Trial and experiment are basically the same thing. But randomized and controlled, what are they? Well, we can't always do them. Like, sometimes... Okay, for various reasons, you can't always do both of them. We like to see both of them. If both of them are there, then the conclusions that we reach are more reliable. They're better analogies. But still, what's randomization and controlled? Well, it's not impossible that, or let's say we saw fewer cold symptoms in the Zicam group than in the no Zicam group. Is that difference definitely due to Zicam? Or could it be due to something else? Maybe it's due to something else. Like, what if it happened that in the group that got Zicam, those people were all young, healthy people, and the group that got no Zicam, they were all old and had other diseases and were just in bad shape. You'd expect the old, in bad shape people to show more disease symptoms than the young and healthy people. So that spread between the outcomes could have been due to differences in the people in the group, not due to differences in the Zicam versus no Zicam. Like, even if Zicam's worthless, and we just gave them, like, fake Zicam or water, you'd still expect to see a spread between those two groups. And what we really wanted to test was, does Zicam prevent colds? Not do age and health status affect colds. We sort of already know that latter one. That's a different question. We're not asking that question. We want to control which question we're studying. Isolation of variables is the science term for that. So there are two ways to do that: randomization and controlled, hence the R and the C in RCT. We'll start with controlled. Ideally, you would want your two groups to be the same and pretty much the same in every way. So when deciding which group someone goes in, you might sort by age and intentionally make it so that the average age in each group comes out the same or almost the same, really close to the same. Maybe you'll make sure the ages come out the same. The weights or blood pressure or something else that affects colds and health would come out the same. You try to make sure that these two groups are as much the same as possible. So that way, if you did nothing to either group and the groups are exactly the same, you'd expect their outcomes to be exactly the same. Almost-ish. Little error, but almost-ish. So if you see a difference between the two groups in outcome, you can be fairly confident that that difference is due to the difference you introduced, the independent variable, the thing you did to that one group but not to the other. That's called controlling for confounding variables, or the C, controlled in RCT. The limitation there is that you can only control, you can't control for everything, and you can only control for things that you're aware of. Things that you even think might have an effect on the outcome. What if, say, somehow, eye color affects susceptibility to colds? I wouldn't think it would. I don't see how it could. And so when I'm designing the experiment, I don't think to control for eye color. That just doesn't seem important. So I don't do it. I forget about it. Eye color, hair color, blood type, favorite color. There's an infinite list of things that you end up not controlling for. All the features about the people that are either too hard to control for, or you don't think are important, or you just never even considered. That's an infinitely long list of things. How do we deal with that kind of uncertainty? Randomization. Aside from the things you're controlling for, you assign people to groups completely randomly. So let's say blood type affects susceptibility to viruses. If you assign people to the groups randomly, and if you have big groups, then statistically, you should have about the same number of people with each blood type in each group. There shouldn't be big differences. If you have large groups, a large study, and you assign people by blood type randomly. And so since the blood types are almost the same, or eye color, hair color, whatever, in the groups, even if blood type does affect susceptibility to colds, that effect should be the same in both groups, and so should cancel out. So if you see any difference, it shouldn't be due to blood type or whatever. That difference is there, but it's the same in each group, because the blood types are about the same in each group. Maybe you didn't think to control for it, but since you assign people randomly, it sort of happened to get controlled for just by random chance. And so by a combination of intentionally controlling for some things that you think are important, and having a big study with lots of people and relatively random assignment to different groups, statistics and random chance help you end up having lots of other features controlled for, sort of, even though you didn't think to intentionally control for them. And so hopefully the only thing that's different between the two groups is the thing that you did to one group, but not to the other group. And that allows us to be more confident in our inference that if and when we see a difference in the outcome between the two groups, that difference in outcome is due to the thing we did or didn't do, as opposed to due to something else. That kind of reasoning by analogy, when we set up our own facts by making two groups and doing one thing to one and not to the other, is what an experiment is. Of course, we can't always do experiments. Sometimes they're technically infeasible. Maybe people don't like you sneezing in their drink and exposing them intentionally to germs and seeing if they get sick. Whether for ethical reasons or practicality reasons, a lot of times we can't do true experiments. What do we do then? Well, really, we watch the next video, because hopefully we don't get stuck. We can do other things.